The majority of today's unmanned ground vehicles are teleoperated, doing what and only what the warfighter directs them to do. While such systems save lives, lack of onboard intelligence limits the range of possible missions and can put operators in harm's way. The Space and Naval Warfare Systems Center, San Diego, has been a pioneer in robotics since early work in unmanned undersea vehicles in the 1960s. The Ground Robotics Program, initiated in 1982, produced a series of teleoperated vehicles performing recon and surveillance for the U.S. Marine Corps, expanding into autonomous security robots for the Army in 1990. The center began supporting unmanned surface vehicles for the Navy in 1999 and later established a focused effort to enhance the autonomy of man-portable systems used in explosive ordnance disposal. The center recently teamed with CCAT, the Center for Commercialization of Advanced Technology, to fast-track the adaptation of several new technologies in support of the warfighter's associate concept, including localization and mapping, leave-behind sensors, standoff radiation detection, and human-robot interaction.
So this poster basically lays out 6 paradigms of human-robot interaction to kind of show you where we've been and where we want to go. Paradigm 1 basically is a teleoperated robot. This is what the Germans used in World War II, and this is actually what we have over in theater today. You have an operator who controls the robot with a joystick, and basically the robot has no onboard intelligence and no sensors. Anything you want that robot to do has to be controlled by the operator. Problem with this is the operator has to carry a very bulky control unit, and secondly, he loses all situational awareness about what's going on around him. If you've ever tried to talk to a kid playing a video game, you'll understand the dilemma. Basically, they don't even hear what you're saying. So this exposes the operator to danger in an environment that's inherently hostile.
Another drawback to teleoperation is that it requires a high-bandwidth communications link. Commercial off-the-shelf RF systems are not optimized for applications involving mobility and generally require an unobstructed line of sight. For example, as soon as the robot enters this underground bunker, communications are lost and the robot slows to a halt. Risk to the human operator is significantly increased as he's forced to relocate the controller closer to the bunker entrance. As the robot penetrates deeper into the underground environment, the video quality typically degrades due to signal occlusion and multipath interference. In addition, when ambient light falls below minimum acceptable levels, the quality can become even worse. A second major shortcoming to teleoperation is limited operator awareness of what is going on around the robot. Even with good communications, it's hard to get a clear tactical picture from a narrow field of view camera situated very close to the floor. Here, as the robot turns to negotiate a doorway, a weapon leaning against the wall in plain sight could escape notice due to lack of peripheral vision. The problem can be further complicated by uneven lighting conditions, such as this brightly lit exit next to a darkened corner.
Paradigm 2 basically is essentially the same thing. You still have a teleoperated robot, but you've now enhanced its ability to maneuver with sensors on board that can detect obstacles and maneuver around them. The analogy is kind of like riding a horse versus riding a motorcycle. If you point a motorcycle at a tree, you're going to hit the tree. Most horses are smart enough to go around the tree, even though you may be directing the horse directly at the tree. So we developed this capability in 1989 in the laboratory. It just hasn't been transitioned down to the user who's operating equipment out in the field. Paradigm 3 we call supervised autonomy. We developed this capability in 1991. And essentially, the robot is now autonomous. It has onboard computers that can help it plan paths and navigate and not run into anything. But there's still a human in the loop supervising the system, filling in for the technology deficiencies. One example is the human has to provide the robot with an a priori map of its surroundings so it then knows how to maneuver from one spot to the other. Secondly, if the robot were to encounter an unknown condition like fire, smoke, flooding, an intruder, the human steps in at that point and tells the system what to do next. Paradigm 4 is what we call full autonomy, and in this scenario, the robot requires no guidance from the human whatsoever, other than a high-level direction as to what you want it to do.
This is a conventional iRobot PackBot chassis, which we've modified with a couple of payloads under the CCAT program, which provide a lot of additional capability. One of the most important capabilities is the ability to sense things in the environment. And we do this for obstacle avoidance, mapping, and localizing the robot. The most obvious one here is a laser, which lets us measure the distance in a 360-degree range around the robot very accurately. We also have a stereo sensor, which lets us do the same thing with a little bit less range, but it also is a three-dimensional sensor, so we get a much fuller representation than just a laser alone would give you.
This new technology has been incorporated in the Autonomous Robotic Mapping System, or ARMS, scheduled for initial user evaluation in 2008. ARMS automates the risky and labor-intensive task of exploration in unknown or hostile environments while providing extremely accurate maps of the structure. The augmented virtuality representation shown here is based upon the Idaho National Laboratory's 3D interface. This map shows walls and rooms with far greater accuracy than a hand-drawn map. Detected openings on the right side of this hallway, for example, are marked with doorway icons for later reference. If communications are lost, the robot can still complete its search and clear mission and then return to the original point of entry.
So basically the key benefit of this system is it allows us to send a robot into an unknown area. It can map it out, find any dangers before the warfighter has to go in there, and it can do that all on its own, even if it loses communications.
Paradigm 5 is what we call semi-proximal autonomy. It's very similar to Paradigm 4, in which the robot enters an unknown area and builds a map and comes back out and provides that map to the operator. And that's a big start in the right direction, but it would be even better if that map were annotated with anything the robot found in there that was of tactical significance, things the operator would want to know about. Explosive residue, human presence, weapons, things of that sort. So in this scenario, we have equipped the robot with more sensors that allow it to detect that type of information and encode it into the virtual model, and then come back out and upload that.
This current setup incorporates 3 different packages. It has a computing payload along with a stick lidar for autonomous mapping, as well as obstacle avoidance and computation. It incorporates a ADCR deployer and leave-behind sensor bricks.
The ADCR deployer was developed as an interim solution to lost communications under the Automatically Deployed Communication Relays program. The deployer module ejects a self-writing relay brick whenever the RF signal strength falls below a predetermined level. With 6 bricks, effective range is substantially extended without increased operator risk. The Bot Drops payload, developed by Corner Turn, uses a reconfigured ADCR deployer module to eject leave-behind motion sensors that can detect anyone re-entering the area after a clearing operation. The robot autonomously explores the structure as before, encoding any found objects of tactical significance into the augmented virtuality model. Once the search is complete, the floor plan representation is analyzed to determine optimal drop points for motion sensor deployment, typically building entryways and hallway intersections. The robot then revisits each chosen location to deploy the sensor units, which are linked together via a low-bandwidth RF mesh network. Once outside the structure, the robot ejects a special terminal node that provides the mesh network with a satellite uplink for reporting any subsequent intrusions. The sensor units shown in this feasibility demo are laboratory surrogates for actual hardened systems currently used in theater. The RadSight standoff radiation sensor, developed by Space Micro, allows a robot to not only detect and identify a distant radiation source, but also determine its bearing. Once an initial vector to the source is detected by the sensor, the robot alters course slightly and takes a second reading to calculate range through triangulation. The robot then moves directly to the source location, correcting its heading as needed. The ability of this standoff sensor to control the robot's search strategy can significantly reduce the time it takes to locate a hidden radiation threat.
We're developing a technology. We've been supported by CCAT with a grant, and the technology is for radiation detection. What the CCAT grant has enabled us to do is something a little bit different. We not only detect and identify that there's radiation in the area, but we also locate where it is.
The term semi-proximal implies that the human and the robot are going to work together as a team now that the threat is known in advance. The robot will accompany the warfighter back into the area of interest, helping to protect him en route. In support of the warfighter's associate concept, the robot currently has 5 different sensor modalities that allow it to keep track of its partner's location. Here we see a following behavior, supported only by the onboard laser. Similar performance is obtained using a vision-based technique. Such sensor redundancy is necessary to ensure reliable performance under dynamic, real-world conditions.
So in the second year of technology transfer program, we've then started to bring in other sensors and mission payloads so that a robot could not only self-navigate in its environment, but also to allow it to sense other things of tactical significance. Our partnerships with INL and CCAT have expanded the number of technologies that we have been allowed to evaluate for the warfighter.
Now, Paradigm 6 is basically identical to Paradigm 5, except that this time the human and the robot go in together at the start of the mission. The technology is matured to the point and is trusted well enough where the human and the robot will go in and act as a team before the threat is known in advance.
In this Paradigm 6 scenario, the robot infers what it should do based on its perception of what the human partner is doing and what the threat is in the surrounding environment. When the warfighter flips off the weapon safety, for example, the robot shifts its visual attention from following its partner to searching for a potential threat. If the warfighter begins firing his weapon, the robot can automatically execute supportive behaviors to shield its partner and/or distract the enemy. The robot returns to follow mode when the weapon is made safe, then automatically initiates another shielding maneuver as the warfighter engages a new threat. Developed by SAIC Englewood, the instrumented airsoft M4 machine gun serves as a laboratory surrogate for similar hardware pursued by the Army's Future Force Warrior program. The Unmanned Systems branch already has extensive experience in the development of automated target acquisition and tracking systems for non-lethal weapons. Obvious synergy can now be realized by merging this advanced fire control software with proximal human-robot interaction behaviors. Here, the robot's weapon automatically follows that of the human partner, allowing its target acquisition system to precisely lock on and track any perceived threat, firing only if commanded by the warfighter. In summary, SPAWAR's technology transfer program, funded by the Joint Ground Robotics Enterprise, was a focused effort to enhance the functionality of man-portable robots being used in theater. CCAT's first contribution toward this goal was incorporating simultaneous localization and mapping for autonomous search and clear missions in an unknown area. This is already scheduled for user evaluation under the Autonomous Robotic Mapping System program. The next improvement takes advantage of an existing deployer module adapted to insert a leave-behind sensor network, which alerts the warfighter to subsequent entry after a clearing operation. Adding the RadSight standoff radiation sensor to the baseline autonomous system allows the robot to quickly locate a radioactive threat. A fourth CCAT effort expedited this feasibility demonstration of hardware, which explores future concepts in sophisticated human-robot interaction.
In about a year, we were able to work with the SPAWAR Robotics Lab to identify areas of interest. We ran a national solicitation. We did due diligence on the applicants, identified contracts to let. We let the contracts and executed on those contracts, and have very rapidly been able to bring these technologies into and integrate with platforms that are being used in the field.
So what's exciting to me is after being stagnated in Paradigm 1 for 65 years, in just 2 years of working with CCAT and our other collaborators, including the Idaho National Laboratory, we have leapfrogged ahead to Paradigm 4, and we have elements of Paradigm 5 and 6 already working in the laboratory, which we didn't expect to see for 10 or 15 years yet.